In this video, I want to talk about the conservation of energy. We're going to do so by using a real simple example of lifting an object, such as this box, putting it up onto a table that's about 0.8 meters above the ground. The box itself has a weight of about 45 newtons, and we're just going to lift the box up. And when we do that, place it up on to the table itself. Place it up onto the table itself here. In doing that, we've now done work to the box. So we have done work to the box, which is the transfer of energy by moving something, and we're going to solve for the work by taking the applied force times the distance we moved it. Since we moved it in the same direction as the force, that's all we need to do for the work. And so our work here is going to be 45 newtons times our height. We lifted it 0.8 meters, and that will give us a work of 36 Newton meters, or 36 joules. Alright, so we've done 36 joules of work to the box in order to lift it up and put it up on the top of this table here. So now that we have the box up on the top of the table here, we can look at the idea of conservation of energy. That 36 joules of work that we did to the box is now stored in the box itself. And so we have 36 joules up here of stored energy. That stored energy is known as potential energy. In this case, we're specifically looking at the idea of gravitational potential energy. That's the potential energy due to an object's position in a gravitational field. So since we lifted the box up, we moved it within that gravitational field since the gravity pulls down, and we gave it some potential energy in this case. And so our potential energy will simply symbolize as a capital P E with a G for gravitational, and we find this the same way that we found work. It is the weight of the object times the height that we lifted the object, or its vertical displacement above the zero potential. We also know here that the weight itself is the mass of the object times the acceleration due to gravity times then the displacement. So we want to find our gravitational potential energy. All we need to know is the weight of the object and multiply it times its vertical displacement. So now we know how much energy is stored up here in the box at this time. So as we look at it now, we see that we have 36 joules of potential energy stored in the box. Kinetic energy is the energy due to motion. As we can see in this case, the box sitting on the top of the table does not have any motion. So right now the only mechanical energy this box has is due to gravitational potential energy. If it did have some motion, we would find the kinetic energy, Ke, by simply taking 1/2 times the mass of the object times the speed of the object squared. So these are the two main pieces that we look at when we talk about the conservation of energy. We want to talk about the total energy. The total energy is always going to be conserved or stay the same for a system. In this case, our system we're looking at our box specifically. So the total energy is just going to be all of the potential energy plus all of the kinetic energy in the system here for our mechanical energy. That means right now the total energy for the box is 36 joules plus 0 joules of kinetic energy because it's not moving. So our total energy for the box in this system is 36 joules. So once we have that 36 joules, and now we know we got that 36 joules from somewhere, that was by doing work to the box. So when we did work to the box, we gave the box 36 joules of energy that it didn't have before, but it came from us, so it's still being conserved. So now we have the box up on top of the table, which has 36 joules of total energy, All of it's currently in the form of potential, but it has 36 joules total of energy. So now we want to look at the box and what happens to it. We bring it off the edge of the table here and let it fall back down to the ground. Alright, so the box is going to fall back down to the ground. Let's say as it's falling along, as the box falls, it will lose its gravitational potential energy. It loses gravitational potential energy. So maybe at this point here, our box has fallen down to a height of only half a meter off the ground. And so then at that point, it's going to have a gravitational potential energy equal to its weight of 45 newtons times that new height of 0.5 meters, which will work out to be about 22.5 joules. So now I have a potential energy of only 22.5 joules at this point right here. So I only have 22.5 joules of potential energy. I started off with a total of 36 joules of potential energy, but now I only have 22.5 joules of energy. The total energy is still 36 joules, so my energy is still 36 joules. The total energy is the potential energy plus the kinetic energy. So I have 22.5 joules of potential energy now plus my kinetic energy. That means the kinetic energy must be the difference between the total and the 22.5 joules, which works out to be about 13.5 joules of kinetic energy. So at this point, right here, when it's fallen about 0.3 meters to this new height, we've lost some potential energy, but it's changed into kinetic energy. And so here's where the idea of conservation of energy is a bit different than many of the other conservation laws that we deal with, in that energy does not just transfer between objects as we saw when we did work to the object, but as it falls here we can see that the energy also changes forms. In this case it's changing from potential into kinetic. Right? The opposite can be true and be said about the fact when we lifted the box up we had energy of motion, which was then converted into energy of position, or our potential energy. So now let's look at the final piece here. As the box then falls to the ground, the very instant just before it hits the ground, all of its energy will be in the form of kinetic energy. And we know that to be true because when it's pretty much on the ground, the height is 0. So if the height is 0, then the potential energy is 0, since it's directly related to the height. So all the energy is going to be kinetic. All 36 joules will have changed into kinetic energy. But what about after it hits the ground? So now it's hit the ground, and we can identify that its potential energy is 0, because it's on the ground, and its kinetic energy is 0, because it's not moving, so the total energy is 0. And so we have to ask ourselves, well, if the energy is conserved, and we had 36 joules of energy, where does the energy go? And so that's the last thing I want you guys to look at, and give me a response to that as the last part of your notes you are taking. Be sure to submit pictures or scans of your notes through today's assignment on Schoology. Here's a hint. The energy can transfer to other objects or change forms. There are at least 3 of those with this example.